Welcome back to McMaster University course Computing and Software 701, Logic and Discrete Mathematics. I am Bill Farmer, and we're going to continue with the topic of first-order logic. Today we're going to talk about the semantics of first-order logic. So let's L here be a first-order language. So as you know, this contains a set of constant symbols, function symbols, and predicate symbols. So what we'd like to do is to come up with a way of giving meaning to these symbols. This is known as an interpretation. So it's an interpretation of our language. And so what we do is we have a domain. This is a set of values that the language is going to be used to talk about. We have a set of values in the domain. These are going to be the interpretations of our constant symbols. We have a set of functions over the domain, and these are going to be the interpretations of our function symbols, and a set of predicates over the domain. And these will be the interpretations of our predicate symbols. So we have the domain, we have a function C that maps every constant symbol to a member of the domain, a function F that maps every function symbol to a function over the domain, and a function P that maps every predicate symbol to a predicate over the domain. So interpretations are also called structures, because an interpretation is really a mathematical structure that plus a mapping from the constants of a language to that structure. So it's a structure plus a mapping. And we can see this easily as if script C, script F, and script P are all finite. Then we can say the mathematical structures is what we have here. We have one domain, a set of distinguished values, a set of distinguished functions, and a set of distinguished predicates. And these values, functions, and predicates are given by these three functions, C, F, and P. Okay, so that's what an interpretation is. An interpretation is a mathematical structure with a domain, and it's a mapping from the symbols of a language to values in that mathematical structure. Okay, now we do have a problem, because what we want to do is we want to assign every term and every formula of our language a value. The problem, though, is we can have formulas like this. X equals 2. The reason this is a problem is how can we possibly assign a value to this unless we know what the value of x is? And x is a variable, so its value can be unspecified or it can range over certain values. In general, it doesn't have a specified value. So how do we give a value to such a formula? Well, the way we do it is we assign all the variables values. And so our assignment of a value to a formula will be relative to this assignment of values to variables. And we call this assignment simply an assignment. And it's an assignment into an interpretation, and it maps every variable to a member of the domain. Now, there's a definition here. We're going to come back to that later. Okay, so now we're ready to do what we're really interested in doing. If we have a term of our language, we want to define what the value of that term is under our interpretation and under an assignment. And this breaks down into three components, or three parts of our definition, because there are three different kinds or three different types of terms. So if we have a variable, we assign as a value of that variable is whatever the assignment assigns to it. And if we have a constant symbol, we assign to that whatever the function c assigns to the constant symbol, whatever value it assigns. And if we have a function symbol application, so f is a function symbol and we have n terms, we assign the value of that will be the value of the function assigned to f applied to the values of each term. Okay, so we're going to do something similar for formulas. So if A is a formula of L, then the value of A under an I and sigma under the interpretation and the assignment is given by the following equations. So for instance, if we have a predicate symbol applied to a set of terms, then the value of that will be true if the interpretation of the predicate symbol applied to the values of all the terms equals true. Otherwise, we assign that predicate application the value false if the value assigned to the predicate applied to the value of all the terms is false. And then we do the same thing for all the logical, same thing for all the Boolean operators. There's a whole bunch of them here. So for instance, for negation, we'll say the value of the negation of A is true if the value of A is false. The value of the negation of A is false if the value of A is true. And the value of a disjunction, A and B, is false if the value of A is false and the value of B is false. Otherwise, the value of A or B is true, and so forth. So far, we've seen that we can assign a value by this recursive definition to every formula. We haven't talked yet about universal formulas and existential formulas. So here's a universal formula. If you think about what it means intuitively, it means that for every value of x, A is true. So how do we make that precise? Well, we make that precise by saying the value of this universal formula for all x, A, is true if the value of A is true for all d, little d and d. But notice I used here a different assignment than this one. So let's go back. That was a definition we skipped. Let's go back and see what that definition says. Here it is. So if sigma here is an assignment, then this is a different assignment, and we get that assignment by just modifying what sigma does in x. So the new assignment, sigma prime, what it does in x is it returns d. Otherwise, sigma prime works just like sigma. So that allows us to define the value of A, where we assign for x the value of d. And if that value of A, when the assignment for x is d, is true for all d, then we say the universal formula is true. Otherwise, it's false. Now, for an existential formula, it's very similar. We look at the value of A, where x gets the value of d. And if that value of A is true for some d, then we assign the value of there exists x, A. We assign it true, otherwise we assign it false. Okay, so to repeat, I'll just write here, we have this way of taking, let me use a little darker color. We have this function that if we give it an interpretation, and we give it a term, and we apply it to a term, this is going to be a member of D. And that's for terms. And we have a similar function for formulas. And that's going to be a member of f and t. Okay, so now there's a whole series of definitions we are going to make. These definitions are very similar to the definitions that we've talked about for propositional logic. So let's say A is a formula of L, U is a set of formulas of L, I is an interpretation of L, and sigma is an assignment into L. Okay, so the first one is sigma satisfies A and I, which we write like this. If the value of A under I and sigma is true. So basically, we'll say that sigma makes A true in I. That's one way of saying it. Okay, then we can say that A is satisfiable in I if there's some sigma that satisfies A in I. So that's what satisfiable means. A is valid in I, or another way of saying it, I is a model of A, and that is written like this. Notice we don't have this little sigma here, and that means that A is satisfied by, or sigma satisfies A in I for all sigma. So another way of saying this is A is going to get the value of true in I no matter what assignment we use. So that's what valid means. And if A is closed, then it doesn't really matter what the assignment is. In fact, it doesn't matter at all. In that case, we say A is true in I if this is true. And in that case, this doesn't matter here at all. It plays no role because there are no free variables. And so if A is closed, then A is satisfiable in I is the same as saying A is valid in I, which is the same as saying A is true in I. All of those are the same. So often people will say something is true in an interpretation. And when they say that, what they really mean is that we're talking about something that is closed, and therefore the distinction between satisfiable and valid is no longer pertains. Okay. Another thing is, if A is valid in I, that will happen if and only if the universal closure of A is true in I. So that means if we have A and we get the universal closure, we basically just put in front of it universal quantifiers over all the free variables in A, then it becomes closed. So in a sense, this formula, the universal closure, and A are both, they're equivalent in the sense if one is valid, the other is valid, and vice versa. And finally, we get the notion of being universally valid. Now notice up here, this was A is valid in interpretation. Universally valid means it's valid in all interpretations. You write this. So a formula that's true no matter what interpretation you have, that is a formula we call as valid, or sometimes people say universally valid. Okay, so now let's talk a bit about sets of formulas. Sigma satisfies a set of formulas in I, which we write like this. If sigma satisfies B in I for all B in this set U. And we will say I is a model for U, which we write like this. If I is a model for B for all B in U. This leads to one of the most important definitions in first-order logic, the definition of a semantic consequence. So A is a semantic consequence of U, which means, roughly speaking, A logically follows from U, which we write like this. A is a semantic consequence of U. We write like this. If sigma satisfies U and I, it implies sigma satisfies A and I for all interpretations I and all assignments U. So that means whenever we can satisfy U, then we're going to be able to satisfy A. That's basically what it says. And we call this a semantic consequence because it's a special form of logical consequence. Now, if U is a set of closed formulas, then the definition reduces to something similar. We'll say A here is a logical consequence of U if every model of U is a model of A. That means in every one way of saying if we have a model, and in that model is interpretation. If we have an interpretation and every member of U is true in that interpretation, then A must be true in that interpretation. Okay, so there's some important metatheorems that we're going to state. Remember, so in first-order logic, we have these formulas, and we later we'll see how you can prove formulas. We'll call those theorems of first-order logic. These are metatheorems. These are theorems about first-order logic. So the first one, the completeness theorem, due to Gödel, 1930. That's when his basic paper was written, but I think he actually proved it a year before that. This theorem says there is a sound and complete proof system for every first-order language. So we had the completeness theorem like this for propositional logic as well. There's also the compactness theorem. This is due to Gödel, 1930, and the uncountable version was proven by Maltsev in 1936. This says if U is a set of formulas of any first-order language, if U is finitely satisfiable, then U is satisfiable. Finitely satisfiable means if I take any finite subset of U, I can satisfy it. And then there's the undecidability theorem, which Church proved in 1936. And this says first-order logic is undecidable. That means there's the problem of whether deciding a formula of a given language is valid cannot be solved with a computer. Okay. Now the last thing I want to do today is to talk about congruence relations. Now this is a rather technical subject, but we're going to need it later. So let's say L is a first-order language, and as a predicate we have E, and this is a binary predicate. And then we have some interpretation. So in this interpretation, we're going to interpret E as some binary predicate. As you know, all binary predicates represent binary relations. So this interpretation of E represents some binary relation. And it represents a congruence relation if the following formulas, closed formulas, are valid in our interpretation. So I'm not actually defining a congruence relation directly, I'm defining it implicitly. It's a little more convenient to do it that way. So if you look at these axioms, what do they say? The first one says that E is reflexive. The second one says that it is symmetric. And the third one says that it is transitive. These say that E is an equivalence relation. Now what do 4 and 5 say? The place you should focus on is right down here. Actually, I didn't draw that quite right. Let me use a different color. Let's focus right in this. this says, if we think of this as the E relation, let's call it equivalence relation, it says that an application of f to a bunch of arguments is going to be related by E to another application of f to different arguments. That's going to be true whenever x1 is related to y1 by E, x2 is related to y1 by E, and so forth. Whenever these are true. So this is saying that if I apply f to equivalent if I apply f to equivalent values, then the applications of f will be equivalent. And there's something similar with the predicate symbol, except here we'll say that this application is equivalent to this if the corresponding arguments are equivalent. Now, when we think of equality, we think of it as an equivalence relation. We think of it working like this. And we would really like equality to work like this. Okay, so there's a couple obvious things to say. I've already pointed out one thing. A congruence relation is also an equivalence relation, and the identity relation is a congruence relation. An identity relation is a relation that says two things are related if and only if they are identical. And often when people talk about equality, they often mean the identity relation. Okay, so I've talked about all this so I can mention an assumption we're going to make. If we have a language like this one where we have a set of predicate symbols, and one of our predicate symbols is equals, the normal equals, we will assume equals represents a congruence relation in every interpretation. So whenever we have equals, we're assuming it's going to represent a congruence relation. So when we just define an interpretation, we don't even have to say what the interpretation, what equals maps to. It will always be a congruence relation. And if we make this assumption, then we get this very nice lemma. So if S and T are terms, A, B, C, and D are formulas of L, then if S equals T is valid in I, then A equivalent to B will be valid in I, where B results by substituting T for S in A. So basically we did an equality substitution. We found the term T in A, we replaced it with T. We found the term S in A, we replaced it with T, and got B, and it's equivalent. So basically we can substitute equal terms for equal terms, and we get equal formulas as a result. We can also do the same thing with equivalent formulas. If C is equivalent to D in I, then we can take A, we can find an occurrence of C, we can substitute D for it, we'll get a new formula B, and it will be equivalent to A. So this is one of the reasons we want to make this assumption about the equality symbol. If we have that assumption, then we get equality substitution, which means we can freely replace terms and formulas with each other if they are equal. Okay, so we're going to stop here and we'll continue.